Okay, so my name is Jared Maupin, and I'm going to be talking about GPU-accelerated streaming uh, using cuStreamz. So I'm pretty much just going to be giving a short introduction, just talk about what cuStreamz is, and then give a bit of a demo. And then I think Chinmay is going to do a bit more of a deep dive after that. So why did we try to accelerate stream processing with GPUs? Other than the fact that we're at NVIDIA, but I think so. We had our data platform that we've been building for a couple of years, and as we were onboarding more and more tenants from around the company, the streaming demands just continued to grow, and I think this is common industry wide. So if we could find a way to accelerate stream processing using GPUs, that would have been excellent for us. So so this is why we started working on cuStreamz. At the time we came up with the idea, we looked around. There was no streaming on GPUs. There was no library out there currently, and because we were a database team and our expertise lied mostly in Python, we built everything around Python as well. And it's open source, so it's open to the community. If anyone wants to go ahead and try it, they can. So I'll talk a little bit about how it works and what are the pieces. So there's three main components. One is the Streamz library, which is a Python-based streaming library, which had a lot of the components we already needed. It had streaming of data frames, and it worked with Dask. But I think the main difficulty we had in a lot of the development efforts went into making the cuDF data frames work well with the Dask and Streamz data frames. So these are the three main components that went into cuStreamz. So with a normal Streamz workflow, you set up your data pipeline and you pre-process data, you do a transformation, and then you do mini batches and you send it to a sink like Kafka or some database. So when moving to Dask and cuStreamz, it changes a little bit. There's sort of like one of the main things that we wanted to do was to move everything to the GPU first. So converting to the data frame was, taking a JSON document, a stream of JSON documents, and converting it to data frames was the biggest chunk of processing. And once the data is already on the GPU as a data frame, then we can begin processing in parallel. So when we move to a cuStreamz or a cuStreamz workflow, like I said before on the previous slide, there's a lot of work here that happens before the processing, before it doesn't get on the GPU yet. So here, as I was mentioning, the data has to be on the GPU so we can utilize the GPU as much as we can. Because once we load the data onto the GPU, then we could, most of the processing is going to be, if we don't load it on the GPU first, we're going to be spending most of the processing doing that. So it's also somewhat expensive to convert data to a GPU data frame. So if we could do that on the GPU as well, then that helps a lot. So I think one of the largest tasks that we had was in our current data platform, we had a Kafka streaming cluster, and we would usually read the data with Spark or some other stream processing framework. So we had to figure out how to get the data from Kafka into the GPU as fast as possible. And what we ended up doing was we wrote our own custom adapter to Kafka that reads data twice as fast from Kafka and loads it in the GPU. And it works out of the box with cuStreamz. Another big effort that we put into cuStreamz was checkpointing. So we had to think, how can we make this work in a production environment? And Streamz didn't have checkpointing yet. So we had to, at the end of the slides, there's a link to how we made this work and how we implemented it, but it was kind of a big effort. Streaming state management on GPUs. So so like I said before, a lot of your processing time is going to be spent getting data onto the GPUs. So if you have data loaded into the GPU already, and you have a state existing in the GPU, then you can get a lot better acceleration with jobs that are stateful. And then again, to support production environment, we wanted to make sure that we can connect to multiple Kafka clusters in case one cluster goes down, and we implement this failover management mechanism. And of course, everything runs on Kubernetes, so it's a lot simpler to deploy. So just to give a summary of the introduction, this is cuStreamz. It's the Streamz library where we have the checkpointing, the robust Kafka implementation, and then in Rapids where we have the Kafka integration and the source connectors to write back to Kafka. So just to run a short demo of just to see it running. So here I have a couple notebooks. It's basically just a word count demo. So I'll just walk through the different parts. So, I mean, in the beginning, we set up our Dask cluster, of course, and then import some libraries. And then we set up the connection information for talking with Kafka. And this is our output code to write back to Kafka. Just flush all the data back. And then in the next two frames, we set up our streams where we read from Kafka. And then let me just go ahead and get this running. So it's running now, but there's no data in Kafka. So I have a producer notebook here. Let me just run this now. So this just produces random words into the topic so that we can read them and then group them. And as you can see, it's working. It's so normally you're not going to see a lot of acceleration unless you're processing millions of records. But this is just an example of it running with only a couple dozen records per second. So yeah, so that's all I have. I think I'm going to turn it over to Chinmay, where he's going to give more of a deep dive.
Let me turn on my video. Can you guys see me? Okay. Let me share my screen 1 second. Jared, I guess you need to stop sharing your screen. Oh, 1 second. Okay. 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 Hi guys, my name is Chinmay Chandak. Thanks, Jared, for introducing cuStreamz and demoing the word count. I'm going to take a deep dive into how we're deploying cuStreamz at scale with Dask. So our whole purpose was to enable data streaming at scale, and cuStreamz enables you to build streaming pipelines with really simple Python API And it has two main scaling components. One is the vertical scaling aspect, which is done by the NVIDIA GPUs and Rapids. That's what we've been talking about so far. So that we use GPUs, you get data onto the GPU, you do all the streaming operations on top of the GPUs. The other more important aspect, as important aspect as vertical scaling, is the horizontal scaling. So if you have a distributed system and you want to deploy cuStreamz at scale, you need Dask. So we're going to take a deep dive into how we're deploying cuStreamz over Dask, and just share some learning, some takeaways as to how, what we learned about deploying cuStreamz in production. So the first takeaway is you've got to use your CPUs wisely. This may come as a surprise, but since you're saying, okay, we're doing GPU accelerated streaming, so why do we need to focus on the CPUs as well? So the problem here is that end-to-end streaming, it has not been GPU accelerated yet. Streaming is a huge and it's a complicated stack. It involves something like reading from Kafka or any other source. It involves some sort of pre-processing, some ETL, some downstream processing as well, syncing to some downstream sync, and something like reading from Kafka, which comprises like a major chunk of your streaming pipeline, is CPU and RAM bound. And this turns out as a significant bottleneck for your GPU processing. So even if your GPUs can, say, process 1 GB per second, but your reading from Kafka is, say, bottlenecked at 250 Mbps, that's going to be like a significant slowdown. So a solution for that, obviously, is to have, since reading from Kafka and such operations are bottlenecked by the CPU, you need to upgrade your CPUs. You can have more cores for high-speed streaming, so you can ensure that the volume of data that gets to the GPUs per second is higher. And you would also need to upgrade your Dask worker memory limits. The second takeaway is using Dask processes versus threads. So a problem that we saw is that there's enough non-trivial control flow in Python, which makes threading more inefficient than using processes, especially in the streaming stack. What I mean by this is that some libraries do not release the GIL. For people not familiar with the GIL, but I guess people are working in Python, so they might. So the GIL is the global interpreter lock, which confines you to just use a single thread like at a time. So even if your thread is multi-threaded, so even if a code is multi-threaded, it is going to confine you to use a single thread at a time. And like a good example for a library that doesn't release the GIL at times is Confluent Kafka, which again works really badly for us because not only is reading from Kafka CPU bound, it's also confined by the GIL constraints. So a solution is use more processes, right? And we did, and we got up to 5x the throughput, like the streaming throughput end to end, if we used more Dask worker processes. Although there's a major caveat here. If you end up creating an arbitrary number of processes, it might not actually work in your favor. The reason is because whenever we create a Dask worker process, and remember, we're gonna, the chunk of processing is gonna happen at the GPU. It's just the offloading data, reading from Kafka is what is CPU bound. So whenever we create a process, it's gonna create a CUDA context on the GPUs, which is really, really expensive. For example, with the cuStreamz stack or with the Rapids and Dask and Streamz, a CUDA context is 400 plus MB at the time we made these slides, and it might go up. So if your GPU RAM has, say, 8 gigabytes of memory, and if you're creating, let's say, 10 processes to get more throughput, you're basically eating up 4 GB of your, basically half your GPU memory just for the sake of it. And that actually leaves lesser GPU memory for the actual streaming operations. You can also use the accelerated Kafka data source that we wrote and Jared talked about, which sort of alleviates this problem and gives a lot more throughput with fewer processes. The third learning that we have was to tune configurations, right? Dask is a huge library. It has a ton of configurations. And in streaming, we, as opposed to most of the pipelines that are using Dask today, we saw that streaming requires the pipelines to run 24/7, right? And there's a lot of components, there's a lot of connectivity issues, and sometimes there might be connection issues between the workers and the scaler. That might happen because of large-scale data transfer or data shuffling like across the workers, or there might be sort of expensive functions that are holding the GIL. There might also be some sort of network connectivity issues. As I said, the pipelines run 24/7, and there's Kafka, there's downstream, there's the GPUs, there's Dask, there's a lot of workers, and that might scale up and down. So there's a lot of components, and connectivity issues are not that big of a deal. A solution to that is use a couple of configs, and tuning them really helped. So there's the distributed timeout configs for both the connect and the TCP. There's a lost worker timeout or like a retry count. And these are just some of the configs that helped us a lot, but they surely do. So takeaway number 4 was worker memory lifetime. So problem here is streaming pipelines can be categorized into like 2 sets. They're like stateless and they're like stateful. By stateless, I mean batches of data come in and you just process them like independent of the other batches. And they're really, these pipelines are complex, but they're relatively less complex than the stateful ones, where we have to maintain some sort of state on the GPU so that batches of data that are getting processed, they need the data or the results from the other batches that have gotten processed or are going to get processed. So with stateful streaming, since there's a state on the GPU and that might increase over time, the worker memory keeps on increasing. Even though Dask flushes out the state, periodically, there's still the worker memory we've noticed creepily sort of increases with time. And the workers terminate after some time, depending on the rate at which you're reading data, maybe after a day, maybe after a week, maybe after a month, but they are going to go out of memory and they restart with a clean slate. And that's cool. But the streaming state maintained on the worker, or the workers, I must say, is lost, which is a big deal because that's the whole purpose in stateful streaming. And a potential solution, and I say potential with caution, because we still have a lot of work to do here, is to use the distributed worker lifetime configs, where you can actually say, okay, just fix a lifetime for my workers, maybe a day, and all your workers are going to stop after a day and restart with a clean memory slate. Obviously, you need to add some sort of stagger config there so that all your workers don't terminate and restart at the same time, so that you have some sort of backup workers to process your data and your job or your data processing doesn't lag. But that's a really cool config that you can sort of play around with. Takeaway number 5 is obviously to use the diagnostics dashboard. I mean, the Dask diagnostics dashboard has been super useful for real-time monitoring, debugging, to see which task is taking how long, what the GPU, CPU, utilization is like. And if you combine with the NV dashboard, so Rapids has an NV dashboard blog on Medium, and it's really cool. It can combine the Dask diagnostics dashboard with the GPU metrics as well, and that gives you sort of like the overall picture of how your system is processing data. Takeaway number 6 is orchestrate using K8s, right? So the entire cuStreamz stack is orchestrated using Kubernetes. We still need to figure out how the autoscaling of workers, the Dask workers feels like. That's future work, but overall, we are running this sort of setup in production. I'll go over that in a few minutes. But just like a simple high-level view, this is how it is. So there's a Kubernetes cluster, there's a scheduler pod, like a Dask scheduler pod, which talks to the workers and then assigns all the tasks in the task graph to them. So there's worker pods. These worker pods are actually the GPUs. The scheduler and the streaming job pod, which actually has the streaming code, are completely on the CPU, so you don't need GPUs there. So the job pod has the Streamz code, which actually has the logic for the streaming job, where to read data from and everything. It submits the task graph to the scheduler, which then assigns tasks to the workers. And the workers are the ones that are actually reading data from Kafka, doing all the processing and everything. And all of this is automated via some of the Helm charts. I think there are sort of existing Helm charts for Dask as well. So we wrote some wrappers on top of the Helm charts and made them more custom to suit our pipelines. So we're running cuStreamz in production at NVIDIA for GeForce Now or GFN. So GeForce Now is NVIDIA's solution to cloud gaming. It's a really cool product. If you like gaming, you must give it a try. So what are some of the cloud gaming use cases that we have at NVIDIA? So this is really, there's a lot of stuff on this slide, so bear with me. So users that play on GeForce Now are either free users or paid users. And the way we look at it is whenever a user plays, they have a gaming session, and the session will have multiple components. It's going to have a session requested time where a user wants to play a game and he's just requested the resource. There is like a session preparing time where you need to prepare the seat on the cloud. There is a session queue time where the user is queued. There might be other users in the cloud and he's waiting in the queue. They're waiting in the queue. I'm sorry. And there's a session playtime as well, which can range from like a few minutes to a few hours. So the types of use cases that we have, they're either stateless or stateful. By stateless, batches of data come in and maybe you're interested in some field, you want to compute the max or average. So they're literally simple. A more advanced stateless pipeline is you get a whole bunch of data, like the entire session file as a zip file, like it has all the events of what happened during the entire session, and you want to compute some sort of quality of service or performance metrics on top of it. And then there's the more stateful pipelines, which are the short window ones and the long window ones. The short window pipelines just build and maintain state for all the sessions for a short time. Say you want to count the number of sessions that are in the queue in any zone in the world at any point of time. And like another long, so the last one is the long window use case where you want to build and maintain state for the entire life cycle of all the sessions. And like a classic use case is to count the number of concurrent users at any point of time. So taking all of these 4 pipelines in production, this is how cuStreamz in production looks like. There's multiple cuStreamz or Dask clusters, which comprise Dask schedulers. There are the scalable worker pods, and there's multiple streaming jobs that talk to each of these Dask clusters. So there might be 1 or more streaming jobs that are talking to the same Dask cluster, and then sort of executing their tasks on top of the workers as well. Talking about the benchmarks, we saw that we got around 3.5 or 4 times total cost of ownership improvement. That means for the same amount of work, comparing the state-of-the-art Apache Spark streaming on CPUs, which is like completely CPU-based, versus cuStreamz, which is GPU-accelerated streaming, we saw that the total cost of ownership, that means for the same amount of work, if you spend like $4 on Spark, you're going to spend like maybe $1 or $2 on cuStreamz for the more complex pipelines, and this is going to save you a ton of money as well. So I'm just going to go over the key takeaways of the talk. There was a lot of stuff that we talked about. So you basically can stream more data for less cost with NVIDIA GPUs and cuStreamz. cuStreamz is basically fully Python based, so you don't need to learn Java, Scala, or anything else. It's literally the same pandas or QDF code that you have, and you just connect it to Dask, you write some simple API, and then you're all set for streaming. cuStreamz is Streamz, which is Python-based streaming, with Rapids, which is like the GPU-accelerated data science libraries from NVIDIA, and there's obviously Dask to scale out everything. And all of this is open source. cuStreamz is feature-rich, so there's checkpointing, so that if your stream job fails, it's going to pick up from where it left off, so you don't lose any data. There's state management so that you can maintain state on the GPUs reliably, and there's the accelerated Kafka data source, which will sort of alleviate the GIL issues or the Pythonic issues that most of us face. To scale GPU streaming with Dask, you need to use CPUs wisely, since the end-to-end streaming stack is really huge, and not all of it is GPU accelerated. For example, reading from Kafka. Use more worker processes, but not too many, because there's a CUDA context created on a GPU per process. And you can tune configs to sort of tolerate the distributed system issues like connection issues between the workers and the scheduler. You need to put tabs on the worker memory lifetimes as well, because memory of the workers can keep increasing, and that might cause issues when the workers terminate. And cuStreamz is Kubernetes ready and is in production at NVIDIA. We've been running the whole setup for close to a year now, and it's been a great experience. And everything is open source. So guys, please contribute, feel free to use, give us feedback. We'd really appreciate it. Some of the cool references, like if you're interested in trying out streaming or GPUAccelerated streaming, that we have a bunch of blogs from Rapids on Medium. Since these slides are going to be public, so you'll have the links to all the blogs. So we have a detailed blog on the demo that Jared shared, which is running word count at scale. There's an accelerated Kafka data source, and there is an excellent blog to get started with cuStreamz as well, and a ton of other blogs as well. Thank you. That's all from my side. If you have any questions, we can take it from here.